Welcome back to this segment on PERT. This is Prashant Bharadwaj again. If you recall, we talked about CPM and PERT earlier. The only difference between CPM and PERT is that in CPM, critical path method, there was only one time estimate for every activity. Whereas in PERT, there are 3 time estimates for each activity. And you can see those 3 time estimates here. If you recall, the origin of PERT was in the US Navy when the first ever intercontinental ballistic missile was being designed in the late 50s. Obviously, it was a very unique project at that time, and the people who were working on that project did not have a good hold on the time estimates for each of the activities. So they came up with different estimates as opposed to one specific time frame for each activity. Now let us look at the 3 time estimates that are used in PERT, and they follow the beta distribution. Let me explain. The one that you would use in the middle is what we call as the most likely time estimate. This is the realistic estimate. If everything goes as per normal circumstances, then this is the time it would take. Okay? Optimistic time is the least amount of time that it would take. So for example, we are talking about foundation for a building. Typically it takes 2 months, 60 days. Optimistic time will be, for example, 40 days. So this 40 should be in such a way that the probability of completing the foundation activity in less than 40 days is less than 1%. So optimistic time of 40 days is practically the least amount of time that you need to complete this activity. Similarly, pessimistic time. This is the longest time that you can take if everything that can go wrong actually goes wrong. So very unfavorable conditions. So for example, in this case, M was 60 days, A was 40 days, B, for example, can be 90 days. So this 90 days should be estimated in such a way that the probability of taking more than 90 days, or the pessimistic time estimate, is also less than 1%. So optimistic time, the possibility of taking less than the optimistic time is 1%. The possibility of taking more than the pessimistic time is also less than 1%. And then in the middle you have most likely. Keep in mind, this is not a symmetric distribution, which means that M need not be in the middle of A and B. So given these 3 estimates, you calculate expected time, or the mean, as given A, B, and M, you calculate the expected time or the mean time as A plus 4 times the most likely time plus pessimistic time, everything divided by 6. A weight of 1, a weight of 4, a weight of 1. 1 plus 4 plus 1 is the 6. Then you have the variance of this. The variance of this particular distribution is given by B minus A divided by 6. Now let's look at a numerical example. The same problem that we had worked on in CPM, which had only one time estimate, now has for each activity optimistic, most likely, and pessimistic times. You can see here an example of asymmetry here. Optimistic is 1, most likely is 2, pessimistic is 9. Same thing here, 3, 4, 11. Whereas some of these are symmetric. It could be symmetric, but it need not be, like you see in these two cases. Now, we saw in the previous slide how to calculate the expected time and the variance. Pretty simple formula. So 1 plus 4 times 2 is 8 plus 1 9 plus 3 12 divided by 6 is 2. Variance b minus a is 3 minus 1 is 2 divided by 6. Square that. It's approximately 0.11. And repeat the calculation for all of these activities. Once you are done with that, the next step is very similar to CPM, critical path method, which you have understood now. Forget about these three estimates now. Just focus on these estimates. Use this expected time numbers as activity times and follow exactly the same process as we discussed in the CPM method and find out the critical path. So once you do that, I won't go through the details because you already know that. The critical path happens to be ACEGH. We have just used the example here in such a way that the same critical path is also here. But that need not be the case. Okay? Once I figure out the critical paths ACEGH, the next step is identifying the probability of project completion within a particular time. Before that, I want to calculate the project variance. The variance of the project is computed by summing the variances of critical activities. So the project variance is represented by sigma p squared, and 0.11, 0.111, 1.78, 0.11. These are all nothing but the variances of the critical activities. If you want to verify that, they are here. So ACEGH, A, C, E, G, H. 0.11, 0.11, 1, 1.78, 0.11. Those are these numbers here. You add them up, you get 3.11. And you all know from basic statistics, standard deviation is the square root of project variance. So take the square root of 3.11 to get approximately 1.8 as the standard deviation of the project. Now, I just want to warn you a very basic mistake many of my students do in the exam or any other place, where they sometimes take the square roots of each one of these and then try to add them up. The standard deviations are not additive, whereas the variance is. So if you take the square roots of individual task variances and get the standard deviations and add them up, they will not be equal to 3.11. Please keep that in mind. Now let's look at the next step. PERT makes one more major assumption, which is project completion times follow a normal probability distribution. That makes it so much more convenient because the normal distribution is beautifully symmetric around the mean. 50% of the time it takes less than the mean, 50% of the times it takes more than the mean. So what is my mean? Mean is 15 weeks. How did I get that? I added the expected times of the critical activities. 2, 4, 8, 13, 15. and the standard deviation is 1.8 weeks, like we saw a couple of minutes back. So I hope all of you recall this. The two extreme points here in the standard normal distribution, this is mean plus 3 times standard deviation. This is mean minus 3 times standard deviation. And that will cover 99.74% of the area under the curve. So practically here, the project will take anywhere between 15 minus 3 times 1.8 to 15 plus 3 times 1.8 weeks 99.74% of the times. Or with 99.74% confidence, you can say that the project takes anywhere between 9.6 weeks, which is 15 minus 3 times 1.8, all the way up to 20.4 weeks, which is 15 plus 3 times 1.8. Now, let me ask a specific question. What is the probability that this project can be completed on or before the 16-week deadline? Okay, so if you look at this, this is 15. This is 16, somewhere here. So I want to know what is the probability that project will be completed within 16 weeks. So obviously the probability is greater than 50%. Why? At 15 weeks or less, the probability is 50%. So 16 weeks or less has to be greater. Going to our old statistical simple formula, z is equal to x minus mu divided by sigma, where mu is my mean or expected date of completion, sigma is my standard deviation for the project, and x is the due date. So 16 minus 15, my expected date of completion of the mean, divided by the standard deviation. So if you do this simple math, 1 divided by 1.8 is 0.56. The z value is 0.56, where z is the number of standard deviations the due date or target date lies from the mean or expected date. So the z value can go all the way up to 3.4, 3.5 in standard normal tables. Okay, so what you need to do then is look up one of these standard normal tables, which can be seen at the end of your own book, and you will find that the probability corresponding to z value of 0.56 is 0.7123 or 71.23%. So you can conclude that the probability of completing this project within the deadline of 16 weeks would be 71.23%. So if you are a project manager and you want to play it safer than 71.23%, what would you do? You would negotiate for a deadline which goes beyond 16 weeks. So let's say you are successful in convincing the customer that 17 weeks would be the deadline. Okay, you can pause here and try to calculate that. What will happen if the due date happens to be 17 weeks? Okay, hope you made the simple calculation. 17 minus 15 divided by 1.8. So the z value will be 1.11. 1.11. If you look at the corresponding value of the probability, you will see it is equal to 0.8665, which means the probability has jumped from 71.23 to 86.65. Now let me give you one last thing to solve. Instead of finding out what the percentage is or the probability of completion is given a due date, what if the manager says, I want to be done with this project with 95% probability. Tell me what the due date should be. In this example as well as the next one that I gave you the deadline 16 weeks or 17 weeks, and then you found out the probability of completion to be either 71.23 or 86.65%. Now, if you are asked what should be the due date if the projected completion date has a probability of completion of 95%, tell us the answer for that. The simple thing you would do is go again back to the normal table and then find out what is the z value corresponding to 95%. Simple. Just change the formula. It will be z times sigma standard deviation plus the expected date of completion is equal to the due date. Instead of looking at the percentage of probability corresponding to a z value, you're given the probability, which is 95%, you find out the z value. Once you find the z value corresponding to 95%, which happens to be around 1.64, you complete the formula, you complete the calculation using the formula due date is equal to z times sigma p plus the expected date of completion. So it will be 1.8 times 1.65 plus 15 weeks. That will be the ideal deadline if you want to be done with a 95% confidence. Okay, this is showing probability of project completion within 16 weeks, like we discussed earlier. The final thing is you don't want to be too carried away, because the non-critical activities also have a variability. We are not taking that into account here. We are taking into account just the variability of the critical activities. I don't want to get into more details, but from a practical perspective, you want to be careful, or you want to be conscious about the non-critical activities and the non-critical paths and their variability. Thank you.